Example F3-1 says the crate has a weight of 550 pounds, and we need to determine the force in each supporting cable. And so from the diagram, we can see that the two cables are supported at points B and C, and they are fixed to walls. And then cable AD supports the box itself. And we are also given 30 degrees for cable AB and a slope triangle for AC. And now the first thing we want to do in this problem is to draw our free body diagram of the system. And since these are cables, we're going to simply have tension forces. And in our free body diagram, we represent the forces as vectors. And so here we have the two forces produced by cables AB and AC. And now since weight is a force, we need to account for the weight of the box in this last cable AD, and that is 550 pounds. And knowing that weight is equal to mass times the acceleration due to gravity, we can just write that as W equals mg. And once again, it's important to remember that weight is directly a force. Basically, if you recall Newton's second law of motion, force is equal to mass times acceleration, which is basically what mg is, mass times acceleration due to gravity. So that's a good way to remember. And now I just need to add the 30 degrees to the free body diagram. And I'll simply label this force FAB. And this other one FAC. And we should always have our coordinate system. And this is simply a 2D x and y plane. And now from the free body diagram, we can clearly see the unknown forces that we need to solve for. And since our system needs to be in static equilibrium, we're going to implement our equilibrium equations where we set the sum of forces equal to 0. So starting off with the forces in the x direction, we have summation Fx equals 0. And so looking at the free body diagram, we see that the forces FAB and FAC act in the x direction. So the x component of FAB is going to act along the x direction. So I'll just label this as FABX. And to clear this up visually, I'm going to redraw the triangle that is formed between the force FAB and its x and y components. Just like this. And so here we can see that this part is cosine 30 and this is sine 30. So FABX is simply FAB cosine 30. And since part of FAB points in the negative x direction, the x component is negative FAB cosine 30. So again, in accordance to our coordinate system, we see that FAB points in the negative x direction. And here I'm just adding in the y-axis and the x. And now for FAC, we have the small slope triangle. So for the x component, we will be looking at the 4. And using proportions, we'll have FACX over FAC equals 4 over 5. So here the 5 is the hypotenuse of the triangle, and that's also FAC. And hence, solving for FACX, FACX will equal FAC times 4/5. Now I'm just going to simplify this W equals mg to just simply 550 pounds. And now back to the equation. We're going to add the FAC x component, which is the 4/5 FAC. And that'll be our equation 1. And now for equation 2, we're going to sum up the forces in the y direction and set it equal to 0. And again, all of this is the actual equilibrium step of the problem. So again, we can see that both of these forces are acting somewhat in the y direction. And so now we're focused on the y-axis. So again, back to the triangle over here at the bottom. We're focused on FABY, which is the y component of the force AB. And so this component is simply FABY sine of 30. And since this force acts towards the positive y direction, it is simply going to be positive. And remember, down here is the negative y direction, which will be important when accounting for the weight of the box. So in the equation here, it's going to be positive FAB, sine of 30 degrees. And now to find the y component of FAC, that is essentially going to be the same process we used for x, except now we're going to be using the 3 instead of the 4, since the 3 is in the y direction. And the hypotenuse is still the 5. And now solving for FACY, we're going to have FACY equals 3/5 FAC. And that right there is simply the y component of FAC. And this force is also in the positive y direction, so it's simply positive. So here it's plus 3/5 FAC. But we're still not done with this equation yet, because we still need to account for the weight of the box since it acts in the y direction. And more specifically, it acts in the negative y direction, so it's going to be negative. And again, since weight is simply a force, we can just simply subtract 550 to our equation. And that right there is our second equation. And now, since we simply have two unknowns and two equations, we can just go ahead and solve for both forces. So here I'm going to take equation 1 and isolate FAB. So I just added FAB to the other side of the equation, which is 0. So this just turns to positive FAB and divide the cosine 30. And so FAB equals 4/5 FAC over cosine 30. And I'll just go ahead and call that equation 3. And so now we just simply sub FAB into equation 2. So that's going to be 4/5 FAC over cosine 30 times sine of 30 plus the 3/5 FAC minus 550, and this equal to 0. And now we can just simply solve for FAC, since this equation is now in terms of only FAC. And so now simplifying the left side of the positive sign, we get 0.4619 FAC plus 3/5 FAC, and then moving the 550 to the other side equals 550. And now simply adding the 0.4619 with the 3/5, we get about 1.062. And so now dividing the 1.062 with the 550, solving for FAC. So 550 divided by 1.062 is about 517.9. And so hence, the force in the cable AC is 517.9 pounds. And now solving for FAB, we substitute the value of FAC into equation 3. So that is simply FAB equals 4/5 times 517.9 over cosine 30. And we just carefully put that into the calculator. And so hence, FAB, or the force in cable AB, ends up being about 478.5 pounds.